Okay, our next speaker is Nick Christians, and the title of his talk is Biochar and Sand-Based Root Zone Modification.
Close enough?
Yep.
Alrighty. I'm Nick Christians. I'm from Iowa State University. My co-worker listed up there, Shane Brockhoff, was a master's student, and this was his master's project. Why biochar and turf? We deal with a lot of sand-based systems. We use something called the United States Gulf Association, USGA, not USDA, system of construction of sand-based systems, which is primarily sand, because the sand doesn't compact and you get good water movement down through it. However, there's trade-offs with sand. Your cation exchange capacity is low, your water holding capacity is low. Generally, we solve that problem with peat, but the idea here was to see if we could do it with biochar. On the left up there is a golf course green, typical sand-based green. Generally, they run in the range of 80 to 90% sand. And more in the last few years, we're seeing that with sports fields. At one time, all of our sports fields were whatever soil they had on the site, but it compacts easily. And as budgets have gone up, they begin to make those out of sand with some type of additive. That is the USGA system. It has a 12, 14-inch root zone on top that is usually 90% or 80% sand. With peat, we can often go 80-20. That seems to be a pretty good mix, but that has to be tested first for saturated hydraulic conductivity and those sorts of things. 90-10 is also common, usually because of the cost of the peat. They'll keep that down a little bit. We then may have what's called a choker layer under that to prevent movement of the fines down into the coarse gravel layer, and then a tile system underneath that. The objectives of the work were to see if we could use biochar in these sand-based systems. We had to test a number of things. We did a lot of work with the soil physics people at Iowa State. We're in horticulture, but they were very cooperative with us and helped us a lot with laboratory techniques. We need to know soil water retention properties. That's one of the big issues. If you got pure sand, the water runs right through it. You can have a heavy rain, and then you've got to water again right away in a day or two. However, you can put too many fines in it and reduce your saturated hydraulic conductivity. Very easy to shut down the pore spaces. You might think you could get by with a 50-50 sand and an additive. That doesn't work. You've got so many pore spaces, so many fines in the pore spaces that it just won't drain. What is the effect on rooting is always the issue. With biochar, we didn't know that. When we went into this, we had no idea if the material we'd be working with was toxic to grass or what the situation was, so that was part of the study as well. We worked with Agrostis stolonifera, which is creeping bentgrass, the primary species on golf course greens. And two, we looked at a number of chemical properties with the materials. The biochar that we used came from the Iowa State Pyrolysis Lab based on switchgrass, and again, that was the Center of Sustainable Environmental Technology at Iowa State University. We set up a very straightforward study. We didn't know anything at all about whether the material would be toxic. We didn't know what it would do to any of our physical characteristics or chemical characteristics. So we set up a series of treatments starting with 100% sand, going 95-5, where the 5 is the biochar, 90-10, 85-15, 80-20, and 75-25, which we kind of assumed was going to be too high. We tried to surround the rates with it. Again, we did a lot of work with that Shane there, but we did a lot of our work over at the soil physics lab at agronomy. They helped us with the hydraulic conductivity and various tests of that type. What did we find? Okay. Number one, the biochar was very effective at increasing plant available water. Over on the left is the 0 biochar going up to the 75-25 at the top there, and we had pretty much a linear increase in water holding capacity. However, there's a lot of other things that are a trade-off here, and one of those is KSAT, which is saturated hydraulic conductivity, which, as we put more biochar in there, filled the pore spaces and decreased the hydraulic conductivity fairly quickly. So if I put the one graph over the other, you'd see they kind of meet in the middle. We were also interested in the effect on the grass, primarily on rooting, and of course if the grass would grow in it, the grass grew very well in it. You have to get up to very high levels to have any kind of a toxic effect. This is a method that we've used for a number of different types of studies. We often do this with herbicides where we're looking at root inhibition with various herbicides. We use a PVC pipe with a plastic liner in it. We put the media inside the plastic liner. We put it on an angle so that as the plants grow and the roots grow down, they will hit that plastic liner, and we can do a non-destructive evaluation of rooting. We can lift those out of there and see as the roots hit the plastic liner. And then at the end, we can do a destructive testing on it to see what the effect on rooting was. And this particular one worked out very well. We surrounded the right rate with a low rate and a high rate very effectively. What that shows is we get a positive effect on rooting to a certain point, which was about 10% biochar and sand, and then we get too much as we shut down the hydraulic conductivity and so on, and probably have some kind of toxic effect on the plant itself. We reduce the rooting. And what we found was that at about 10%, 90% sand, 10% biochar, we got the best effect. And if you remember the water holding capacity going up and the hydraulic conductivity going down, that crosses at about that 10% line. Chemical properties. We looked at the leachate, the electroconductivity, the pH, the total organic carbon. We did a lot of nutrient analysis on this, and we did nutrient analysis on the sand at the end of it. What did we find? First of all, pH. You heard some of that this morning. The pH would be expected to go up, and it did. This was already a fairly high pH media. Well, it is a high pH media. It was a calcareous sand, which has a native pH of 8.2. Now, this is leachate, so we don't get an 8.2 coming out of the leachate. But as you can see, as we increase the amount of biochar, it had an increasing effect on the pH of the leachate. The phosphorus in the leachate, we did pick up a lot of nutrients from this switchgrass biochar, more than I had anticipated. And this is the same rates again, going up to 25%. We had an increasing amount of phosphorus available to the plant, an increasing amount of potassium available to the plant. Conclusions, biochar definitely increased the water holding retention, which is very important to us, because if we build them out of pure sand, and we do build golf course greens and sports turf out of pure sand, in areas where water is not an issue, like up in Ontario, Canada, and New York, and areas like that, they will build what they call the California-style golf greens and California-style media for sports fields. They're pure sand. But you've got to run an awful lot of water through them, and you have to adjust your fertility program accordingly. So we are interested in increasing the water retention to some extent. Biochar decreases saturated hydraulic conductivity, as you would anticipate. As you get more fines in the pore spaces, it shuts it down very quickly. With peat, we can usually go up to about an 80-20, 20% peat mix. We found with the biochar, probably because of the finer particles and the interpacking in the pore spaces, we were about 10% was as high as we wanted to go with that. Biochar did decrease rooting depth of creeping bentgrass in media containing more than 10% volume by volume biochar. So we went up to 10%, we saw a positive effect, and then starting at the 20%, we saw a little bit of inhibition, although they were pretty close, and then an obvious negative effect as we went higher. Biochar also increased leachate electroconductivity. I didn't show that for the sake of time. Total carbon. And as you saw, it did provide essential nutrients. We also did some work on the tissue content of nutrients, and they went up as the leachate did. If anyone would like more information on this, there's a thesis on it that I can make available as a PDF. It was also published in Agronomy Journal, and then we had a popular article in Golf Course Management. So all of those, you can find me at Iowa State, and I can send those to you very easily if you would like them. Or I have them, I guess, on a memory stick today if you'd like them. Any questions? That should get you almost back to time. Yes? Plant available water. How did we do that? Let me think. Okay. We had the pressure chambers. I didn't show that, but again, I got a lot more slides on this. Where we mix up the media, we put it in the pressure chamber, we take it down to field capacity, and then we can take it down. We have a very thick-walled chamber. We can take it down almost to wilting point. So those were done in that way. That was actually done in our lab. We have the equipment for that. Yes?
So how long did the study go on as far as leaching? I mean, is this over one season?
No, this is not over a season. His question was, how long did the study go on with the leaching? Those leachates were from the tubes, and that was, I think, 12 weeks is the amount of time that we went on that. We also did some from repack columns over in the soil physics lab. So we had various methods on that, and that's all spelled out in the thesis.
Nick, I have a question for you.
Yeah.
In terms of your leach phosphorus amounts, do you have any feel for how much of that was percentage-wise of the addition from the biochar? So like, did you leach 50% of what you
Okay,
had?
his question is on how much of that additional phosphorus is from the biochar. I don't know if I can pin down the precise amount, but it's almost all, because the sand is very inert. Now we did have to put some fertility treatments. So we used a modified Hoagland solution to get them started. So there was some additional phosphorus in there, but most of that's coming from the biochar. Yep.
We'd have time for one more question.
Yeah.
How much reduction you were able to get with the nitrogen fertilizer application?
How much?
Reduction in nitrogen fertilizer?
Oh, how much? Okay, his question is how much were we able to reduce the nitrogen fertilizer with the biochar? We weren't able to determine that. I do have some data on nitrogen leaching and nitrogen uptake, but I would not be able to put a figure on that. But clearly, the biochar would contribute to the amount of nitrogen that we're putting down to the plant. That would be a good additional study, probably in the field, to see how much we could offset the nitrogen requirement. Nitrogen requirement is considerable in that kind of environment because you've got rapid water movement, you've got leaching, you've got no organic matter basically, so it is a very important issue. Oh, yeah.
I realized the application of biochar is to use the root development. So is that because the biochar gives you better water holding capacity, so they kind of inhibit the root development, or there's some toxicity?
Okay. That's his question is with the reduction of rooting as we went up with the biochar, is that due to the reduction of hydraulic conductivity, or is there some kind of toxicity? We asked the same question. We don't know for sure based on the results we had from this study. I'd say it's a combination of both, but I think there is clearly some toxicity, some excessive amount, and I'm not sure if it's nutrient or what it is, that was probably setting the root system back as we went up. But I really can't determine from this study. Yeah. pH is another factor, right? We've got the increase in pH, and what other elements are in there that we didn't measure. There could be some toxicity like that. We were just interested in whether we could grow grass in it and how much we could put in before we did damage. And above 10%, we got damage. You got time for one more? Yeah.
Did you also look at the effect of like how much biochar you need so that you don't get the soil compaction?
His question is, did we look at the effect of increasing biochar on soil compaction? We have a carefully sized sand to start with that won't compact, so that's why we build it out of that. So we wouldn't. You can run heavy equipment on it and many soccer games, many football games without any compaction. So I wouldn't anticipate that the biochar would reduce the amount of compaction. That's already part of the physical characteristics of the sand. But when we do that, when we choose sand of those particle sizes, we very easily get interpacking into the pore spaces, and then we shut down hydraulic conductivity. So everything's a balance.
Let's thank Nick again.
Okay, thank you.